Hello everybody, Mr. Gustin here. Today we're going to be looking at horizontal launch problems. So we talked a little bit today in class about projectile motion. This is one kind of portion of that projectile motion. It's called the horizontal launch. And what a horizontal launch means is an object that is launched with an initial horizontal velocity but no vertical velocity, like this object right here. I'm going to show you a little setup here. I have a little mini ramp here. I have a marble. I'm going to take the marble and launch it down this ramp. Now watch to see why it's called a horizontal launch type problem. Right there, you can kind of see as the marble leaves the ramp, it leaves the ramp so with just a horizontal velocity and no vertical velocity. So today, we're going to take some notes, but really our job is going to be to predict where on the floor this marble hits the ground, okay? That's going to be the goal here, is to try to find a spot where this marble hits the ground and determine where that spot is without doing anything but a few measurements and a little physics. So here we go. Let's go ahead first and take some measurements. Let's see how far this object is going to fall first. I've got my giant meter stick here. I'm going to measure how high this object is off of the ground. When it falls, it looks like it's about 104 centimeters. Okay? So I'm going to come over here and record this. I'm going to have some measurements. I'll take some measurements in the horizontal direction and in the y direction. These are going to be my knowns. So the height, so I know it's going to fall. My initial y velocity is going to be 104 centimeters. So I'm going to call it 1.04 meters. My final y velocity, or y position rather, is going to be 0. It's going to hit the ground. I know that my initial velocity in the y direction is going to be 0 meters per second. And I know that because it leaves the ramp going exactly horizontally. And then lastly, I know that my acceleration is equal to baby g, or negative 9.8 meters per second squared. All right, excellent. Let's look and figure out what I know about the x direction. Now, I don't know how far it goes. That's what I'm looking for, right? That's kind of what my unknown. I am looking to figure out how far it moves horizontally. So it's change in x. That I don't know. I also don't know the time. I'm not sure about the time that it falls or the time it moves horizontally. I don't know those things either. I do have one more tool here. I'm going to allow myself to use my BSB here that will take the velocity of the object as it leaves the ramp. So I'm going to get an initial velocity here of the time it takes, or the velocity of the object as it leaves the ramp. So we'll see if we can do this. All right, it looks like it was traveling at 1.11 meters per second as it left the ramp. That's my initial horizontal, that is my horizontal velocity. So initially, my x initial is 0 meters, but my x velocity is going to be equal to 1.11 meters per second. And remember, over here, no acceleration in the x direction. Okay. With the primary goal in mind of solving for change in x, I think we need to draw a model. I think we need to go ahead and kind of sketch a model of this scenario on the board and go ahead and start breaking some stuff down. So I'm going to move you over there. Here is my scenario. Object leaves the ramp with an initial x velocity. It travels its way off of this table and lands somewhere over here. This distance here we'll call delta x. This distance here we'll call delta y. I'm going to call this my origin over here at 0 meters, 0 meters. But let's start solving. What do I need to know? Well, if I'm trying to find delta x, I know that the only model that governs this motion, this horizontal motion, is that change in x is going to be equal to the velocity in the x direction times the time. Great. I know that I start my initial position at 0. I know that my initial velocity is 1.11 meters per second, but I don't know anything about time. I'm stuck. Let's try something else. So I know I need to find time horizontally. This is kind of the key that will unlock this solution so I can put my target in the right spot on the floor. Let's try a different thing. Let's try the y direction. If you remember from class, we said that these two motions, projectile motion is motion in which there's an object moving horizontally and vertically. And the most important word I think here is simultaneously. The reason that word is so important is because simultaneously means that time in the x direction is equal to time in the y direction. An object will move horizontally for the same amount of time that it falls for. As soon as that object hits the ground, it's no longer moving vertically or horizontally in free fall. It has just come to a stop. So, if I can find time in the y direction, I might be able then to unlock this problem and find time in the x direction, and then find my final displacement. Let's check this out. What are some things I know in the y direction? I know initial and final positions. I know initial velocity. Again, the initial velocity is 0. It was dropped vertically from rest. The only velocity we had was horizontal. Lastly, I have acceleration. If I look at my list of equations, to try and find time, knowing position. If I know position and I want to find time, I think I need to use my quadratic. This is the equation that governs the relationship between position and time. Let's start plugging some numbers in. The initial velocity in the y direction is 0. That goes away. I know from my data that my change in position is negative 1.04 meters per second. That's equal to 1/2 times negative 9.8 meters per second squared times t squared. I'll give you a minute to solve that problem on your own. Solve for yourself using your calculators what you think time is. I'll solve it myself, you solve it yourself, we'll compare answers. When I solve this myself, I end up with time being equal to 0.46 seconds. This is the time the object is falling for. The time it takes for the object to get from the surface of the table to the ground vertically. Now, like we said before, this time is also the same amount of time the object will move horizontally for at its speed of 1.11 meters per second. I can go ahead and now take this time, plug it into my constant motion equation, and solve for the change in x, or the displacement horizontally. I end up with my change in position being equal to 0.51 meters. So, when asked, where should I place a target on the ground so that the ball will launch off of the ramp and hit the middle of the target? The answer is 0.51 meters from the base of the table. Let's go ahead and check this out. Let's see if we can do it. You can kind of see the ramp there. Here's the floor. I'm going to measure my distance. .51 is right there on the ground. 0.51 is right there. Now I may be left or right of this target, but I'm going to place that target on the ground. Let's see if you can see my target. There it is. Okay, I'm going to place this fancy carbon paper on the ground right here. All right, let's see. Let's see if we can get this object to hit that spot. Oh, and look how close we were. That mark is right here, right next to my tape. I just missed it a little bit to the right. Awesome. That is so stinking cool. All right, folks, so you've got a little bit of an example problem up here on how to solve these horizontal launch problems. The keys to remember with a horizontal launch is that the initial y velocity is 0, and that always during projectile motion, the time in the x direction is equal to the time in the y direction. Good luck on the rest of worksheet 14.